Welcome back everyone, this is Advanced SQL Chapter 6 and our discussion of recursion in SQL. I think our initial training regarding recursion in SQL is complete now and we are fit to tackle one of the first larger tasks in this course. And well, this particular task is related to a data analysis task that you will find, or very often find, implemented outside the database system, which is a pity because the source data that these algorithms work with are often located inside the database system. So what this normally means is that there is some effort of data serialization, data transfer, and then reparsing of the serialized data at the site where the actual algorithm will be implemented. And this, of course, means, well, additional effort that we would rather love to save. So that relates to this summed down here. And, well, there is a class of algorithms, and we will be looking at one particular algorithm here, the k-means algorithm, which is often connected to machine learning problems and algorithms, where there's, of course, libraries and pre-built systems that can implement machine learning problems. But, well, these machine learning libraries, or ML libraries as I call them here, are often implemented as main memory-based systems or main memory-based algorithms. Large data sets that we try to analyze may easily overwhelm these main memory-based frameworks and challenge the limits of the data volume that these frameworks can process. And well, that's a homemade problem because the data was residing in the database in the first place. If we only could move the computation, the k-means algorithm, for example, close to the data inside the database system, then we would save the data serialization, parsing, and related efforts, right? And well, we would be operating in an environment that has been designed from the ground up to work with large data volumes. And this is exactly what we are trying to pursue. Actually, that is what we are trying to pursue in the entire advanced SQL course. View the database system as a capable environment to express advanced computation. Do not, as your first gut reaction, select start from table, externalize all the data, ship it somewhere else, and perform the computation elsewhere. No, try to execute complex computation close to the data. And all of the upcoming examples, this k-means example including, are actually testament to the capabilities of database systems to express complex computation in an efficient and, I think, also very elegant fashion. All right. So enough of the sales talk, let's see what k-means is all about. It's a data clustering algorithm. All right, so in k-means we are given a set of, well, multi-dimensional points because we are talking slides here and looking at these two-dimensional slides. Well, we will be looking at two-dimensional points for this example. But of course, we could talk about n-dimensional data in general. Right, so these n-dimensional or two-dimensional points given in the 2D plane here, they are supposed to be clustered into k clusters. This k is an integer that has been predefined, that has been given. So we are looking for a separation of all the points into 2 clusters or 4 clusters, where if k is 2 or 4. So that would be input to our clustering algorithm. All right, once the clustering is done, we expect each point in our data space here to be assigned to the cluster with the nearest mean point. All right, so if we look at this particular set of data here, we would probably expect 2 clusters if k is 2 that are located like this. I would say this would be one possible outcome. And if you look at the mean of this particular cluster, so probably this point, can I draw? Yeah, and maybe this point. Well, these points are located in their respective clusters because the mean of this particular cluster is nearest to each of these points. All right, so P2 is of course nearer to this particular mean point than this particular mean point. And this is true for all the points and the clusters and their mean that have been computed by the algorithm. All right. So this is the expected outcome for k equals 2. And of course, it could be different for other k here. Right. This is a very powerful clustering algorithm, but it's computationally difficult, even NP hard. That means that with the number of points and the number of k increasing, we are facing a really tough problem. But, well, there is good approximations and good heuristics around that perform clustering to a quality and to a degree that makes it computationally feasible and practically usable. And exactly at one such approximation we will look here in this course. Right, so what we will look at is Lloyd's algorithm for the computation of the k-means clustering. Lloyd's algorithm with a particular type of initialization of the entire algorithm, which is called the 4G initialization. So Lloyd's algorithm plus 4G initialization, these two together, they form a pair that you will almost always find out there if it comes to a practical usable implementation of k-means clustering. And exactly this pair of techniques we will try to implement using recursive SQL here. All right. So how would we start? How would we start the entire thing? What does 4G initialization mean in this context? Well, we would pick k points. K is the number of clusters that we want to define. So for our example, let's pick k equals 2, right? Okay, so k equals 2. We would pick k random points, 2 random points in this example. That would, and those would form the initial means, cluster means. All right. As you can see here in my example, I've picked P5 and P6, these black points, as being the initial cluster means. Okay. Well, how would we proceed then? Well, in 2 steps. In the first step, we would look at all these 7 points here and would assign each of these 7 points to their nearest mean. Okay, right, so I think this will probably lead to an assignment that looks like this. So P4 is closest to P6 here. All other points, including P5 of course, they are closest to P5. And that would be the first initial assignment, of our points to clusters. This assignment would now be refined and iterated. Well, we would look at the assignment that we've just found and compute new means, the average point, the mean point inside each of the 2 clusters that we have now defined. And probably that mean would probably lie here for this lower cluster and probably lie here somewhere for this upper cluster. This is the update phase. So given this initial assignment of points to clusters, compute new means, or as they're called here, new centroids for each of the clusters. All right. So based on these new means, we would then perform a new assignment again. And again assign each of the points to, well, this was the one mean and this is probably the other mean. Would assign each of the points to their nearest mean again. And well, in this particular setup, this will probably mean that well, these points are forming one cluster and these points are forming one cluster. All right. And well, then we would again proceed to compute new means and so forth. The new mean will probably lie somewhere here for this cluster and lie probably somewhere here for this cluster, and so on and so on. So that would be the iterated assignment and then the update of the actual current centroids for each of the clusters that we've defined. in iterative fashion, right? This will go on until the assignments of points to clusters no longer change. Well, if the assignments no longer change, then the means, the centroids will no longer change, then everything becomes stable, and the assignment that we have found so far would then be the output of this particular algorithm. Well, I've tried to sketch the assignment or the updated assignment of points to clusters here on the slide. I've of course prepared the SQL code that performs this this iterative assignment and update procedure, and I've also prepared an ASCII-based, character-based rendering of how these points are being assigned to clusters and how their clusters change. And there you will, I think, much better appreciate the dynamicity and the progress of this particular algorithm. All right. Right, so, first things first, how would we implement this particular step? Like, given a set of points, pick k random points and make these the first initial cluster means. So how would we implement this 4G initialization in a sense? Well, and there is multiple ways to do that. Well, of course, we would need a table of points. A table of points that would be the representation of our data space, of the two-dimensional grid of points that we've seen before. And we would just use the built-in point type of PostgreSQL to implement just this. Well, it fits so well, so let's use the two-dimensional built-in point type to represent our initial data. And that would be located in table points. From that, we would have to pick k rows, k points, at random as the initial cluster means. And well, this would be two possibilities, two different alternatives to pick such random selection of points from a given table, right? We could, for example, order all the rows by some random variable. All right, so we would just reorder or shuffle the rows in a sense, and rely on the source of randomness built into PostgreSQL at this particular point. And once we've done that, we would just first pick the first k rows from this random reshuffling of all the rows. That would be one possible assignment or one possible set of points that we could assign as the initial cluster means. Another method would be quite specific to PostgreSQL. This is not mentioned or implemented in the SQL standard. It's a table sample function that indeed picks a particular selection of rows from a given table T, and there is different methods to sample a set of rows from a particular table. The Bernoulli sampling would just pick s% random rows from the overall extent of rows in table T. So this s here, well, we could pick s so that it represents the k rows, the k clusters that we want to form, and that would be a different method to perform the 4G initialization of our algorithm. Right. Okay. Well, then it's already time to implement the iteration, the recursion that is the core of Lloyd's algorithm. So what would be our query plan here? What would be our query plan to implement Lloyd's algorithm? Again, we are thinking in terms of invariance, like we have done so many times already when it comes to the solving of recursive problems in SQL. Okay, so we would probably construct a recursive common table expression, and this recursive common table expression will compute a table called k-means. Since Lloyd's algorithm proceeds in different iterations, well, we would capture this particular iteration that we are currently computing. We would capture this explicitly in table k-means. Later on, when we look at the resulting table k-means, we would have column iter, or this first column here, to check how the assignment of points has changed from the 4G initialization through the first, the second, the nth iteration. it would be our task to supply the algorithm with the maximum iteration, like after n iterations, I'm content with the assignment of points to clusters. That would be one possibility, and that is the first one that we will implement. But when we could also implement Lloyd's algorithm to its true words and iterate until the assignment no longer changes, right? So this would be the conceptually cleaner and probably the more reasonable version. There is some considerations there that have to be taken, and we will do this in a second step here. Okay, so much for the iteration. Right, so in each iteration we would look at each of the points of the 7 points in our example, of each of the points in our data space, and in this table would record to which cluster we have assigned this particular point. Cluster C would be just a cluster identifier, probably some integer that identifies the cluster, an integer between 1 and k. Right, the mean of this particular cluster C, it would be in column mean here. So M would be a point. M would be the centroid, the mean of cluster C here. Right, and that would be the meaning of all of these 4 columns. There are no more columns to be maintained in our table k-means. Of course, for all clusters, for all rows that belong to one particular cluster C, the mean in that particular cluster will be identical, right? So there's only one mean in cluster 1 and there's only one mean in cluster 2, but many points will be member of cluster 1. So all of these rows for these points in cluster 1 will store the same mean. This is what I'm referring to as the embedded functional dependency between columns cluster and mean here. Again, we happily accept this at this particular point to keep the computation clean and simple. Full normalization of the data would probably call for an external representation of the mean outside this k-means table. I think that would be an unwise choice in this particular case. We will live with the embedded functional dependency. I only wanted to hint you at this well, slight redundancy that we are facing while we are computing the k-means. All right, I think this is all about the data layout. Of course, in the first iteration, in the zeros iteration, right, after the 4G initialization, well, there will be only 2 entries, 2 rows in this particular, or k rows. There were only k rows in this particular table, namely the k points that we have elected to be the current cluster means. From iteration 1 onwards, so iteration 1, 2, up to the maximum number of iterations, in each iteration you will find all the data points. All the data points will be represented in table k-means in each iteration with their assignment to a particular cluster. All right. Okay. I think it's time to look at the SQL code again. Right, and as it has become common now, all of this stuff fits onto a single slide. Right, so this is only the Lloyd algorithm part. I do not show the 4G initialization here. That would be found here at this particular point in the query. We will see the entire code when we switch over to the terminal. All right, so Lloyd's algorithm performs an iterated assignment and update step. And exactly these 2 steps, the assignment step and the update step, they are found here in the SQL query too. So there is a nice conceptual mapping from the idea of the basic idea of the algorithm to the SQL code. All right, so in the assignment, we would look at all the points and we would look at all the current means that we have assigned. So this is the recursive reference and this is the reference to our input data. So we would look at all the points and for each point would look at all the current means, right? And order these points means pairs by their difference, by the distance of the point's location and the mean's location. And of course, we are interested in the minimum distance between some point k and some cluster k's mean. All right, and well, to do that, we would just use the old distinct on trick that we have used so many times already at the beginning of the lecture. All right, so of all these points and means combinations, right, for each point, look at the mean with the minimum distance and pick exactly this particular combination of point P and means K, cluster means K. All right, where this distance is minimum, well, we would just pick the point, we would pick that particular cluster ID. Of course, that would be the location of the point that we have just picked, and we are in a particular iteration. Of course, we start in iteration 0 and would then later on maintain that iteration and assign and increment this iteration. So that would be the assignment. Each point would be assigned to the cluster and its mean where the distance is minimal. All right. So given this in this subquery table assign, we would then proceed to the update stage. All right, and we would iterate over this assignment of points to cluster means, right? Would just reproduce that here. Point has been assigned to a particular cluster. We would maintain the iteration. Of course, we are building a new assignment. We are building a new assignment or recording a new assignment of points to clusters. This is the next iteration of the Lloyd's algorithm, and as such, we just assign the increased iteration counter here. And of course, inside the cluster, we would compute the new centroid, the new mean, which is just the average x and y coordinate of all the points that belong to a particular cluster. Well, that's easily done. So we would just look at all the points inside the cluster. You see that we are using this over window here, over cluster, right? The window cluster is just a partitioning of all the assignments that we have found by cluster. All right. This is exactly what the task of look at each cluster in separation and find the new centroid inside each cluster. This is exactly the semantics of what look inside each cluster means. It's a partitioning of all the assignments by cluster. Inside that cluster, we would find the new average x coordinate and the new average y coordinate for all the points that we have assigned to that particular cluster. And from these average x and y coordinates, we would simply create a new point, the new mean of this particular cluster. And that's all there is to it. Well, we would be operating in the back-based semantics here. We will see that over when we switch over to the terminal. And as such, we have to make sure that this code at one particular point will produce no rows at all. That would be the signal to the iterated back semantics of our recursive common CTE to stop computation. And well, you see this particular where clause here, which is here to implement just that. We would look at the iteration. How many iterations have we already performed? If this exceeds the maximum number of iterations that we were planning for, that we were prepared to invest here for Lloyd's algorithm, if this exceeds the planned iteration, well, then no row, no assignment that we have just created will actually pass this predicate, and the entire query will produce 0 rows. So after the planned number of iterations, we will indeed leave the computation here. As I told you already, this is a very practical and usable way to enter computation. Of course, it requires us to predefine a number of iterations that we are willing to wait or willing to invest into Lloyd's algorithm here. Maybe we would rather have the algorithm be so flexible that it leaves or ends the computation once the assignment is stable and does not change anymore. We can indeed implement that, but as I told you, there is some more considerations to take here, and we will do that in a second step. Right, so first let's look at the first step, at this particular version of the code. And as such, it's time to switch over to the terminal. Here we are. You see that this is indeed a version of the code where we have to predefine a number of iterations, and I will do that here. Let's use 4 iterations in this particular example. Right, then let's prepare the points table, the source of data that we want to cluster and assign to the K clusters. Right, so this is the points table. Here is an instantiation of the points table with 7 rows. These are exactly the points that you've seen on the slide. So what we will see here in the computation in the terminal directly reflects the problem instance that you have seen on the slides. So this is our points table. As you can see, all of the points are identified by automatically assigned IDs, and this is their location represented as the built-in type point built into PostgreSQL. All right, this is the source. Well, now let's look at the k-means algorithm. There first would be the 4G initialization, and we haven't shown this on the slide, but it's very simple. This would be the base case query, the query Q0 as we've already called it, in our recursive common table expression. So let's look, what are we doing here? Well, we are looking at all the points, and we would normally at random select k points from this set or this table of points. Well, k is 2 in our slides, and it shall also be 2 in the example that we are pursuing here. So I'm picking 2 points from this set of points, and it's the points 5 and 6, which is exactly the 2 black points that we have picked on the slide. So no randomness here. I want to have an example here that I can show you that directly mimics the situation on the slides. I could have also used the table sample method or the ordering by random, just as we discussed a few minutes ago. Okay, so these 2 points will lead to 2 clusters that are being formed. Right, so these 2 points have been picked in the zeros iteration. All right, so these are the points that have been picked. I will assign cluster IDs just by numbering the points that I've picked here. Well, this row number will just assign the numbers 1 and 2 in this particular case. Of course, if we pick more rows here, then that row number would assign unique cluster IDs for all of these picked points. Well, since these clusters only contain this particular single point by this time, the location of the point also is the mean of this particular cluster. It is time. And that would be the base case query already. Okay. You haven't seen that on the slide, but now it's complete here. What you've seen on the slide is everything below this union all, right? So the union all, as I told you, we're operating in bag semantics here with an explicit control of the number of iterations. And well, this is what you can see here. This is exactly the query that I've shown you on the slide. I think there is actually no bit has changed here. It's actually the same character by character, so no need to discuss this further here. All right, yeah, so well, we could just run this. I've also brought some code to perform some visualization of the stuff so that we can follow the iterated assignment and then the k-means update, the update of the means of the k clusters. And I will show you this visualization in a minute. Because the details are not relevant to the actual computation of the k-means, which is already complete once you reach this particular line, I've just folded them away. You could open the folds and then look at what you find there. It's not particularly complicated or deep code, so let's not bother with that at this point. So what we will instead do, in the first step, let's look at the raw table k-means, the recursive common table that has been computed by our recursive CT. And there we go. All right, so let's look at the output here. It's iter point cluster mean, exactly the 4-column table that we have expected. In the zeros iteration, we have 0, 5, and 6 to be the means of the clusters 1 and 2. These are the means of these clusters, and these are, of course, the locations of the points 5 and 6. Afterwards, after iteration 2, after iteration 0, I am sorry. So starting with iteration 1, and then also 2, and 3, and 4, which would be the final iteration, as we've defined at the top of the file. After iteration 0, you will find the assignment of all the 7 data points to their respective clusters. So in iteration 1, all of the 7 points have been considered here. These are the point IDs. These are their assignments to clusters currently. So 2 points are being assigned to cluster 2, 5 points are being assigned to cluster 1 now. These are the new means. These are the new means of these clusters. Okay, here you can see the embedded functional dependency. All of the points, all of the clusters are, of course, equipped with the same mean, right? So this is the functional dependency here. All right, so that would be the first iteration of our Lloyd's algorithm. In the second iteration, things have changed already. The assignment has changed. You see there's only 4 points now in cluster 1 and 3 points in cluster 2. The means have changed in iteration 3. Well, now cluster 2 has become the bigger cluster, all right? While the bigger cluster has been 1 in all the previous iterations. And in the fourth iteration, indeed, there's only 2 points in the cluster 1 and there's 5 points in cluster 2. So the assignment really has been swapped around and everything has been shuffled. These are the final cluster means that we are being left with. And this is the final arrangement of points or assignment of points to clusters. It's perfect, because nobody can read this gibberish of points and floating point numbers. I have prepared this visualization I've already mentioned. So let's activate this. Let's disable the output of the raw data. Let's enable the output of the rendered data. And I will now just repeat this particular query and look at the result here. All right, so indeed, this is again subdivided into different iterations, right? So this would be the iteration 0, and as you can see, all the points are present. All of the 7 points are present. 2 of these 2 points have been elected as the current cluster means, right? So there's 2 cluster means and 5 residual points that are separated or distributed in our 2-dimensional space here. That would be the zeros iteration. In the first iteration, you see that points have already been assigned to their respective clusters. So these 2 points at the top here, they have been assigned to cluster 2. All of the rest has been assigned to cluster 1. Given this assignment, we can compute new cluster means. So indeed, the cluster mean of cluster 2 has wandered to the top here, and the mean of cluster 1 is located as a centroid between all the points that have been assigned to cluster 1. This changes in iteration 2 already, when we find that this particular point, which is it? That this particular point is indeed closer to this cluster mean than to this cluster mean, and so this will change now. Its assignment will change, and of course the location of the means will change. Right, so this is the third iteration, where you can see that the means of the first cluster wanders towards the bottom left here of our two-dimensional space, while the means of the second cluster approaches the center of the data space. And in the fourth iteration, you would find that indeed the center of the cluster 1 has identified 2 points in the bottom left here as being members of one cluster, and all of the other points are being clustered in, well, cluster 2. And I think this would also be the intuitive clustering into 2 clusters that we would consider by just looking at the data visually. All right, so 4 would be the final iteration that we consider at this particular point. So that would be one implementation of Loy's algorithm with 4G initialization to have an implementation of k-means clustering inside the database itself without shipping the data to some external algorithm system that performs the clustering for us. Okay, so back to the slides. There is a few more notes I want to make here. Actually, it's a few notes, but also a few grievances. So things that I would love to do, I would love to show you in this first iteration of the query, but I'd rather not, because it would complicate things. So one thing is in the code, when we create the new cluster mean, what we do is, well, we deconstruct the points and their locations into their explicit x and y coordinates here, using the square bracket notation to access the x and y coordinates. We have done that before. And given these, we then compute 2 separate average x and average y coordinates using these 2 partition averages or window averages, right? Only to then later construct a point again from the x and the y coordinates that we have computed. So we would first deconstruct the points and then later construct a point again. And well, this is less elegant than you would hope for. What you would probably hope for would be something like this. I give you a bag of points. Please compute the average of this bag of points, the centroid of this bag of points or this set of points, and return the centroid. Well, there is no such average aggregate over points. Well, that's a pity. We could define one, and indeed I've brought a second version of the code with me where I used PostgreSQL's ability to define user-defined aggregates to create an average aggregate that works just like this. I think this would make things more readable and more elegant. All right, this is one observation. Another observation maybe is more important here, and that would be our discussion of the explicit specification of the number of iterations before we start the clustering. This is unsatisfactory, I would say. K-means is really the prototype of an algorithm that searches for a fixed point, for a stable assignment of points to cluster that does not change even if I iterate further. This is actually the core, the nature of the K-means algorithm and Lloyd's iteration. Still, we don't do that here. We use union or semantics, the bag-based semantics in our recursive CTE, and we manually maintain and then test a column iter, which is really something that is questionable, right? Well, the reasons behind that are rather mundane. To use the set-based semantics, the union-based semantics, we would need an equality operator on points. Okay, to decide whether 2 points that we have found in one point in an earlier iteration of our CTE and 1 point found in the most current, the latest iteration of our CTE, whether these points are equal or not, whether this constitutes new data that we have found in the last iteration, or whether this is something that we have already seen before. In that case, it would have to be removed using set difference from the result of our last iteration. For that, we would indeed need an operator, a Boolean operator, to decide the equality of 2 points. There is no such operator built into PostgreSQL. Maybe to your surprise, at least to my surprise, there is no such equality operator on points in PostgreSQL. Well, we can rectify that, and we can define quality on points in user-defined fashion. So that's what I've also done. We could just define equality on points our own, supply the system with this new equality operator, this new notion of equality, and then it could, regarding the points, it could use the union-based, set-based semantics of the recursive CTE. So that would be one check mark that we could set. We could also disregard points and simply work with explicit x and y coordinates. So instead of using the nice abstraction of a two-dimensional points, we could just maintain the x and y coordinates as two separate, whatever, integers, floating point values in separation. These values, they are equipped with equality, and they could be handled by the set-based union semantics of the recursive CTE. That is the second option I'm mentioning here. I think this would be a pity, and it would be the inferior option. So in the solution that I will show you in a minute, I've opted for user-defined equality on points. Then our implementation uses a strictly increasing iter column, an iter counter that helps us to tell the different iterations apart. This is indeed crucial to identify the assignment, the latest assignment that we have found during our computation. Without this iter counter, it would be hard to spot the final assignment of points to clusters. So that iter counter serves a purpose, but of course it spoils the computation of any fixed point. Because this iter counter is strictly increasing in each iteration, we will never reach a fixed point. The iter counter will be higher, will be one higher than in the last iteration, and we will never be able to reach a fixed point. So that would lead to endless recursion. This is a real conundrum. And again, the user-defined operations or types in this particular case in PostgreSQL could point to a way out here. So what I've done is I've defined a particular type, which I also call iter, which behaves like a counter, which I can use to perform just arithmetics like +1 or something. I can just do integer arithmetics on this new type iter. But if the system looks at the equality of two iter values, well, I've defined equality on this type to always yield true, regardless of whether one iter value would be 3 and the other iter value would be 4 in the next iteration. Regarding the system, these values 3 and 4 would be equal. All right, so we could indeed reach a fixed point. The system would indeed see that no relevant new information has been computed in the last iteration, and it would still lead to the end of the recursion. Okay, so let's look at this trick that I've implemented there. It's implemented in the k-means set SQL file, because this is implementation of the same k-means algorithm but in set-based semantics. Okay, so what I'm doing here is defining equality on points, as I told you, and an average aggregate on points that computes the centroid of a bag of points. So let's do that. Quite some stuff going on there, as you've just seen, right? Of course, I will distribute the points.sql file where you'll find all of this stuff. You are not supposed to dig deep into this file and understand all the necessary details. Please look at the file if you're interested. Otherwise, just assume that it defines equality and this average on a bag of points. And I've defined this new type iter, a new type iter that behaves like an integer when I try to implement counter arithmetics, but otherwise always compares to true, regardless of the real iter values that I'm looking at, so that I don't spoil fixed point computation. Okay, so I've done that. Let's look what we got here. So what we got here is equality on points now. So we expect that this is indeed true. And the equality on points works now. This has not been available before in PostgreSQL. Okay, so that would be false. All right. And then there is this new iter type that looks like an integer but really isn't. So let me compare two iter values here, and you will see that the system regards them as equal. Right? Of course, 3 and 3 are equal, but 3 and 2 are equal as well. All of these values are equal, so they won't spoil the fixed point detection. Okay. I can also do arithmetics with these guys. So I've always to be very explicit about the type assignment here, because otherwise the system switches over to integer arithmetics. This is not what I want. So what you can see here is that indeed it's still true, and still I can perform arithmetics. Okay, so this is exactly what I need in this particular case. All right, so given that, well, we would proceed as before. We would have our base table of points. We would have our initialization, or 4G initialization of our k-means computation. You see that the table remained the same. It's still the 4 columns, right? We would make sure that, of course, the iter values are indeed of type iter now, and everything else actually remains the same. It even becomes simpler, as you can see, yeah, here. All right, so this is just the computation of the new centroid of the points in the current cluster. No need to deconstruct the points first, and no need to then later construct a point from the average x and y coordinates separately. I would just use this aggregate or window function in this particular case to compute the centroid over all the points in the current cluster. Nice. It's even simpler than before. And if I let this run, and you can see that there is no mention of any particular explicit iteration counter here. We will rely on the system to find the fixed point itself. Indeed, we are using the set-based recursive CTE semantics here. Performing that would lead to the very same result, and indeed, after 4 iterations, the assignment of points to clusters has been stable. We now see that, and well, could use this final assignment as the output of our k-means computation. All right, I think this is already the longest video that I have ever produced in this particular course, but there's one final slide here. Final slide here. I've been asked before, when I demonstrated this SQL implementation of k-means clustering, whether this formulation of the algorithm really is the nicest formulation that you can have. There's this subquery inside the assignment, the first step of our Loy's algorithm, that uses the distinct on formulation and so on. And well, is this the nicest formulation of the assignment of points to clusters? I would rather have something like this. I would iterate over the points, right? And for each point P, I would then look at the means and find the cluster K that with its mean is closest to the current point P, and then would pick its cluster ID. All of this is very well and good, and this is of course very readable code. I would love to write that, but it's not possible to do that. It's forbidden. A reference of the recursive table, k-means, as you can see here, inside a subquery that is located in the select clause, is forbidden by the SQL standard. We will come back to this in a later example, but well, this formulation of the query is indeed forbidden. The placement of the recursive table reference, k-means in this particular case, is restricted in many ways, and this would be one restriction. Placing the k-means reference inside a subquery in the from clause would be fine from the viewpoint of the SQL standard. It may not occur in a subquery in the select clause. All right, that would be the very sad answer at this particular point. We will have to say more about restrictions of this particular kind, but this truly is something for an upcoming video. We are at 50 minutes now. Oh my god. All right, so let's draw a line here. This is k-means clustering using SQL. I hope you found that enlightening. See you then. Take care.